Good afternoon, Scott here, known as Cantaloupe to some online, and I'm bringing a video to you on a subject that's interesting to me. It might be of interest to you or someone you know. This is going to be a feature of the library I've been working on and developing towards graphics in WebGL, and a very specific detail that this library supports that may not be widely known. I don't think the graphics library itself is widely known, but it's a feature that I use actually, and I want to describe what it does because it's unique in the sense I have never seen it in any other graphics library, and it's kind of an improvisation on the idea of averaging normals. If you're into 3D graphics design and programming, you might know what I'm talking about with normals. You have a vector that is perpendicular to a face or facet that is a triangle or polygon on a model, and these vectors, these normals that are just usually unit length, that's a unit length is 1 unit long, whatever the unit is that you're using, it's perpendicular to the surface of the polygon, if you can imagine that. So it's a triangle, for example, the normal for a triangle would be extending from either the vertices themselves or the center point. Doesn't matter. Normal can exist anywhere on a plane or polygon and is perpendicular to it by definition. So you can take a surface made of polygons, such as with a model that you generate or create yourself in a program like Blender or 3ds Max or Cinema 4D. I'm not sure what all the modern ones are, but you can create a 3D model with lots and lots of polygons. It's usually how they're made up, and then you assign normals to those polygons for shading, for things like lighting and reflections. These are calculated based on the normals typically. And you can even do what's called averaging, which gives you, instead of like a disco ball effect that you would have otherwise, if you average the normals, that is the vertices that are shared between polygons, if you average them and then give each normal that averaged vector direction for all of the shared vertices, if that makes sense, the ones that are coincidental, the ones that are in the same location, you end up with a smoothed normal surface. So that gives you, it takes away the disco ball effect, and it gives you a very smooth shading, which is, it's kind of a trick of math. You don't actually reduce the number of polygons or increase the number of polygons, but you do smooth out the effect that is created by the normals with this averaging. Now here, the point of all this is, there's a point. When you average your normals, it can be a very computationally intensive operation depending on how many polygons you're dealing with in your model. You might have, thousands of polygons, and to average your normals, you have to recursively loop per polygon through all the other polygons to get those averages, which isn't a big deal in terms of complexity or difficulty, but it can be a performance problem. It could be prohibitively computationally intensive to do this every frame. Here's the thing. Now, when you're creating an animation or a game with a complex model that has more than, say, 100 or 200 or 1,000 polygons, averaging all your normals per frame is very quickly a bottleneck for performance, and it will destroy your ability to create something with a decent frame rate if you're trying to average things that are changing in shape. So usually what happens is they're pre-computed. The normals are averaged beforehand because you can do that at your leisure and then just include the data in a file or whatever. But this becomes problematic when your model is, like I said, changing shape. If it's something that is designed to have like a video height map, which is something I'm getting into. I've been creating these height maps that can be based on a video or some kind of formula, some kind of dynamic formula that is changing over time for a modulated surface. Your normals aren't going to look right unless they're recalculated. So what's the solution here? And this is what I'm getting to. In my library I'm working on, I've included and developed a way to pre-associate the normals based on their indices within that model. So while your model may be changing shape, the number of polygons and the associations between the normals themselves doesn't usually change. Even if the shape is changing, the ones that are coincidental are still going to be coincidental, it turns out, pretty much all the time. So I have a custom internal format that my library uses. It's a JSON-based format that can be exported to a file. There's an option, and I'm not going to get too deep into all of the various options, but there's a way to export any shape that you create in this API to a file. And when you use this custom format and you have configured your shape or model to associate normals, that is to pre-compute, you can add a switch, an optional configuration switch to pre-compute your normals. And if you have also chosen to average them, the shape that gets exported, this custom format, will include not just the averaged normals, but also the associations, which is useful for what I said. If you are going to use this shape as a dynamic base that has, for example, a height map that is modulated based on a video or whatever, if the shape is expected to change shape, and you want to be able to quickly and efficiently recompute all of your averaging, your normals, so that it computes the reflections and shading correctly while it's being animated in real time at a high, performance, reasonably performant frame rate, you can do that with this custom format. And the format doesn't really have a name. It's just, like I said, it's a JSON file. It's got the raw dump of the vertices, the UVs, the normals, and optionally, and that's the point of this video, the associations between the normals. I cannot overstate how difficult and performance breaking it is to try to average your normals per frame without those associations. And it's an undocumented feature at this time. I might, go into it later on, but that was the purpose of this video, just to introduce the concept of pre-associating your normals so that they can be very quickly averaged. It turns out the associations are what take the long time. If you're going to average your normals, if you think about the process, it's the recursive looping through your shape, trying to figure out which normals are coincidental. That takes a long time. That's the deal breaker there, the performance breaker. So if you can pre-compute the associations, you don't have to find them every frame. They're already in your file. They're already potentially, saved in memory, which once you load the new file that you've saved as a shape, it loads the pre-computed associations from that file. And then if you call the built-in method sync normals with the optional switch to average them, guess what happens? It is transparently, seamlessly fast. It's full frame rate. In real time, you have all of your reflections, you have all of your shading, your Phong shading, even if your dynamic shape is changing shape. So it's one workaround, and it's one feature that I have not seen in other APIs. So I'm kind of proud of it. I've been using it a lot myself, and I just wanted to describe it a little bit. If any of that made sense, you probably have a little bit of background in computer design or programming. So if it's something you're interested in, please reach out with questions or comments to whitehotrobot@gmail.com. Thank you.